Hello, I am Brendan Yee and my group mates are BEATRICE Wong, Benjamin Yeo, and Brendan Tan. Here is what we will be covering in this presentation. Let's start by discussing the core requirements of aerospace materials, focusing first on the strength-to-weight ratio. The strength-to-weight ratio is a critical property of aerospace materials. Lighter materials are crucial in aerospace for several reasons. They reduce fuel consumption, increase range, and allow for greater payload capacity, all leading to cost savings. Next, let's examine key mechanical and environmental considerations. Fatigue resistance is essential, as it prevents cracks from forming. Fracture toughness allows material to resist crack propagation, the increase of cracks. Additionally, temperature and environmental resistance are critical for materials exposed to extreme conditions, such as high heat and corrosive elements. Components like turbine blades rely on these properties to maintain structural integrity under challenging conditions. Finally, we'll discuss safety and longevity, which are closely linked to fracture toughness. Damage tolerance and stable crack extension. The material's ability to resist crack propagation is crucial, so as to avoid sudden catastrophic failure. We want to keep the crack growth rate as low as possible to reduce the need for repairs, extending the component's operational lifespan. For common aerospace materials and their characteristics, we will be talking about 5 main types of materials, mainly aluminium alloys, titanium alloys, carbon fiber composites, ceramics, and superalloys. Aluminium alloys have a high tensile strength with low density, together with good corrosion resistance. Aluminium alloys are commonly used in aircraft fuselages. Titanium alloys have a very high tensile strength of up to 950 megapascals and is significantly less dense than steel, making it a useful material for components that have to withstand large amounts of force, like the landing gears of aircrafts. Moving on to carbon fiber composites, they are extremely lightweight, giving them a high strength-to-weight ratio and has high resistance to changes in temperatures. They are favored in the aerospace industry as they are very versatile, as many other materials can be incorporated with carbon fiber to serve different purposes, and are mainly used in fuselages and wings of both aircrafts and spacecrafts. Ceramics are materials that are neither metallic nor organic. Ceramics possess extreme resistance to corrosion and temperatures as well as high structural strength, allowing them to be used in components that experience high temperatures and stress. Popular ceramics include silicon carbide, silicon nitride, and are often used in jet engine turbines and heat shields in spacecrafts. Finally, superalloys are made of 2 or more elements, created for high strength, resistance to temperature, and corrosion. Superalloys have an extreme resistance to deformation and can remain functional in temperatures as high as 850 degrees Celsius due to its high thermal stability. They are often used in jet afterburners and combustion chambers as they can withstand extreme conditions such as high temperatures and oxidative environments for prolonged periods, allowing for an extended lifespan of key aerospace components. The selection of materials is crucial to ensure overall operational efficiency in an aerospace vehicle. Here are 3 factors we look out for: flight efficiency, safety and reliability, and cost efficiency. Firstly, using materials like aluminium alloys, titanium and carbon fiber composites reduce the overall mass of the vehicle, directly lowering fuel consumption. This is crucial in aerospace, where fuel efficiency is a major determinant of both performance and cost by extending its range and load capacity. Secondly, aerospace vehicles have to resist compressive forces of air pressure and remain structurally reliable in extreme environments, from the intense heat during re-entry to the freezing vacuum of space. This protects the occupants on board and the integrity of the vehicle. Lastly, aerospace vehicle manufacturers aim to maximize output with minimal inputs. Despite the initial expense of material production, they lead to significant cost savings over time by consuming less fuel on lighter vehicles and the longevity of durable materials. Finally, we will examine the future trends in aerospace materials. Firstly, biomass carbon fiber is created by carbonizing precursors obtained from biomass derived from raw materials. This could provide a viable alternative to carbon fibers obtained from oil-based precursors, and research areas even include algae. Secondly, thermoplastics may be heavily utilized as it can be up to 10 times lighter than metals and outperforms metallic components in terms of corrosion and fatigue resistance, insulative properties, and durability. They also contain a non-corrosive base with low water absorption, allowing for natural buoyancy. Thermoplastics are also inherently flame resistant. Lastly, we have nanomaterials. For example, carbon nanotubes, one of the strongest materials known, could be used to make stronger and lighter spacecraft structures, while nanoscale sensors and actuators could help spacecraft autonomously adapt to changing conditions in space. Carbon nanotubes also have potential for use in space elevators due to their high strength-to-weight ratio. In conclusion, aerospace materials require high standards for performance. Key materials include composites, ceramics, and superalloys, each providing properties like corrosion resistance and high tensile strength. Mechanical properties such as fracture toughness and fatigue resistance ensure durability, flight efficiency, and safety. Innovations in new materials are constantly being explored to improve overall performance. Thank you.